Hello guys, welcome to the channel. Today I have a really fun integral with a really nice identity and proof. So let's just dive straight into it. Cool, so here's the integral and I actually prepared a hint. So I'm just going to pause for a moment for anyone who wants to try the integral without the hint. Cool. So the hint I prepared is to use King's rule. So if you know it, you can apply it. Cool. And if you don't know it, then it's maybe worth searching up and trying to use it. And I'm just going to pause for a moment for anyone who wants to try with the hint. Cool, so let's dive straight into it. So here's the integral, and just quickly before I get into using King's rule, I just wanted to say that there's actually a really nice identity, which is if you have a very particular set of properties, which is if you have an even function on the numerator, which we have here because x is an odd function and sine x is an odd function, so two odd functions multiplied will make an even function. Um, and then you have on the denominator, you have kx plus 1, um, where kx is a function where kx times k to the minus x equals 1. Then you and this is an identity you can use. So we have e to the x on our numerator and then kx plus 1 on our denominator. You can then, and our bounds is a and minus a. That's also very important. Then you can do, it will simplify to this. So you can save yourself a lot of working and just go here if you know that identity. If you don't know that identity, then we're going to go into a proof of how this works using King's rule. So yeah, let's dive straight into it. The thing with King's rule is we set our integral to equal I or any variable. And whenever we have a new variable, we can chuck a box around it because it's quite handy. And then King's rule is saying that I is equal to j, where j is this. So what King's rule says is that wherever we have an x, add if we add both of our bounds um, and subtract x, then the integral will hold true. And there's a nice proof for that, but we're just going to go with that it works. Um, and then you can see that pi minus pi is going to cancel out. So then you're left with a situation where you have minus x sine minus x over 2 to the minus x plus 1. And this is where we can start taking advantage of the properties of our function. Since we know that x sine x is an even function, then we can then say minus x sine minus x will equal x sine x. So that's really handy. So now we can then swap out our minus x's for x on the numerator, just like so. But our denominator still needs a bit of work. We have 2 to the minus x plus 1. But there's this really nice trick, which is then if you multiply both the denominator and numerator by 2 to the x, just like so, then j will simplify to this. And now we can see that we have the same denominator with j as we do with I, but we just have this 2 to the x. But there's something really nice, which is we can then add j and I, just like so. So here's my I from here, and here's j. Um, and then since we know I is equal to j, we can then say this is 2i, because I plus I is 2i, like so. And also we can add, imagine x sine x with x sine x 2 to the x, because you can just add integrals, like so, and there's a common denominator, so there's no problem there. And you're left with this expression here, or this integral, sorry. And then what we can see is that these 2 to the x plus 1s will cancel out. And then we can also divide both sides by 2 to get I is equal to half of the integral between minus pi and pi of x sine x dx. So that's really nice. That's a really nice way of navigating it. And there's the identity mentioned earlier is a really nice identity to know because it will save all of this working out. And then from here, it's just a matter of integrating by parts. So if we just say u is equal to x, and u prime is 1, and then v prime sine x, so v is equal to minus cos x. So then by parts says that this integral will equal vu minus the integral of vu prime dx. Just like so. So v is minus cos x in u, so that multiplies to minus cos x, minus x cos x, minus u prime v, which is just 1 times minus cos x, which is minus cos x. And then you keep remembering our bounds and remembering our half as well. And then just to simplify, we have minus and minus, so we can write that as a plus. And then this looks a lot cleaner. So now we just need to integrate cos x, which cos x integrates to sine x. So then you will produce these brackets with our bounds. And now it's just a matter of plugging our values in. So if we plug in pi and then subtract the plugging in of minus pi, just like so, you get all of this. Again, remembering our half, very important. And then it's just a matter of simplifying. So we know that sine pi and sine minus pi equals 0. So we can just ignore them because adding or subtracting 0 won't do anything. And then we can take advantage of the fact that cos is a even function. So then we can, since we know that cos x equals cos minus x, it's a symmetrical function, we then know that minus pi cos pi is equal to minus pi cos minus pi. And so it simplifies like so. And then we see that there's a 2 and a 2 times a half is just 1, so that will cancel. And then you're just left with minus cos pi, minus pi cos pi, and cos pi is minus 1. So minus pi times minus 1 is just pi. And so that's our final answer. So we can chuck a box around it. And there you go. I really do hope you enjoyed, and I look forward to seeing you guys next time.